Okay, so in example 24, I am requested to prove that by manipulating the left-hand side, which is obviously the more complex of the two sides, I can manipulate that left-hand side to be equal to the right-hand side. And the only thing that I can do is either distribute and remove my brackets, or possibly that cotangent and that tangent I can replace with my reciprocal or ratio identities. I think at this point in time, it doesn't really matter which direction you go, it just matters that you start. I'm going to distribute. So I'm going to multiply sine t cosine t times each term inside of the bracket. So therefore, when I do so, I get cosine squared t times sine t times cotangent t minus sine squared t times cosine t times tan t. Again, it doesn't matter what order the cosine squared times sine times cotangent is in, other than they're just all multiplied. So nothing really to simplify there, other than now I'm forced to address the cotangent and the tangent, which is partly why I put it last in the two multiplications. I know that cotan is the same thing as 1 on tan, but considering I've got sines and cosines everywhere, I would prefer to use my ratio identity. So it's going to look like this. Cosine squared t times sine of t times that cotangent is going to be changed to cosine t on sine t minus sine squared t times cosine t, and again that tan is going to be replaced with sine t on cosine t. And again, nothing to do with that denominator. And what you can see at this point now is these fractions, cosine sine, that sine in that denominator is going to cancel with that sine. This cosine in that denominator there is going to cancel with that cosine. So what that leaves me with on the top is cosine squared times cosine. So unfortunately, cosine cubed t minus sine squared times sine is unfortunately sine cubed t. And again, nothing to do with the denominator. So if I look at what I've got on my right-hand side above, I recognize that I don't have a fraction on my right-hand side. So therefore, it leads me to believe that that cubic thing on the top must factor. So I need to recall that if I have a cubed minus b cubed, I've got this thing that we called SOAP in order to help us factor. SOAP was uncubing the first term, uncubing the second term. The S for SOAP stands for same. I had a cubed minus b cubed, so therefore that's a minus b by the SOAP acronym. Square the first. Opposite for SOAP is why I have plus. Multiply the two together, a times b. And then SOAP, AP is always positive for the last term. So plus your last term squared. So I need to remember how to factor a cubic, otherwise I can't go any further with this identity that I'm meant to be proving. So uncube the cosine, so that's cosine t. Same, uncube the sine, so sine t. That's my first set of brackets. Square the first, so cosine squared. SOAP is opposite, so now plus. My first times my last, so cosine t times sine t. Always positive for my last term, and square my last term. And again, nothing to do with the denominator. No simplifying there. But if you're observant, you've already noticed that that first bracket of cosine minus sine will cancel with the denominator, which is good. Again, that was what we wanted, because when we go up and we compare to the right hand side, there's no fraction on that right hand side. So therefore, luckily, by factoring, the denominator canceled out. So I'm left with cosine squared plus cosine t times sine t plus sine squared. And for those of you who know your Pythagorean identities quite well, you'll recognize that cosine squared times sine squared is a Pythagorean identity. We know that that equals 1, so therefore those two terms can be replaced with 1, which, if we compare that to the right-hand side, that equals the right-hand side, which we were requested to prove. So thus we have proven QED.